Today we're very happy to have Noah Miller, who's going to tell us about soft graviton theorems in Bfss. Take it away.
Okay, thank you. Thank you so much for inviting me. Very happy to give a talk on this paper. So feel free to ask any questions anytime. I think the talk would probably work better like that. There's a lot of disparate stuff in this talk, so hopefully we can have everyone understanding as much as possible. Okay, so BFSS is like an explicit example of a flat space holographic duality. And whoops, how do I? Okay, and the main, I would say maybe the main goal of this paper is just to fill out this holographic dictionary. So BFSS is a duality between M theory in 11-dimensional flat space, which has supergravity as a low energy limit, and that includes soft gravitons and asymptotic symmetries. So what are the manifestations of this on the other side of the duality, where we have this 0+1 dimensional matrix quantum mechanics? So in order to talk about both of these things together, I'm going to introduce what asymptotic symmetries are, then I'm going to briefly introduce what BFSS is, and I'm going to talk about the paper. So there's this general motto that the asymptotic symmetry groups, which I've written with MathCalG, are gauge transformations which preserve certain fall-offs or boundary conditions modulo small gauge transformations which have compact support. So just a really basic example in U1 gauge theory. So if you define the retarded time as U, which is just time minus the radial coordinate r, and then you write the metric in these coordinates. And then you have this index A, which is different from the gauge field, but that's just the sphere. So A equals 1, 2, this is the metric. Then there are certain fall-offs in 4 dimensions that the radiative gauge fields will satisfy. So the U component will have some sort of fall-off, and the R component will have some sort of fall-off, and then the angular component will have some sort of fall-off. And you can find these fall-offs. So these are the fall-offs for U1 gauge theory. So we have these fall-offs. If U and R go as 1 over R, and then the angular component goes as O1, then if you have some function, which I've called theta, which is parameterizing some gauge transformation, then under this gauge transformation theta, these components of the gauge field A are going to change for each component. And in order to preserve these fall-offs, we need to find a very specific thing, which is, to leading order, so O1, the U derivative of theta has to be 0, right? And that comes from, can you see my mouse?
Yes.
Okay, and that comes from this thing here in particular. So I guess I could have written partial U theta is O of 1 over R, but just to leading finite order, the U derivative is 0, right? Because we need the derivative here to be 1 over R. So we have these U-independent gauge transformations that preserve the fall. So we have a non-trivial asymptotic symmetry group parameterized by functions on the 2 sphere. So for the total general gauge symmetry A mu, if we use the action of the gauge field coupled to some external source, one can compute the conserved Noether current for this parameterized by this gauge transformation theta, and I mean that is the Noether current, which happens to be the divergence of a 2 form. But there's a lot of, so I'll just say that there's a lot of misleading stuff in the literature, especially old literature before this whole soft theorem story was worked out, where people said, oh, Noether currents from gauge transformations, these are trivial, they're not physical. That's totally not true. They're slightly strange. They're divergences of 2 forms, but they're totally meaningful, and especially just the asymptotic ones. But okay, so if you just sort of integrate this Noether current over null infinity here in the future and then here in the past, then you have some sort of process that happens in the middle. It's charged particles scatter and they'll release radiation, and you have these 2 Cauchy surfaces, future and past null infinity. and you just sort of take, the QF, the final charge has to equal the initial charge. And if you, if you write all this out, you'll find that it's actually the soft photon theorem. So that's what these asymptotic, this is a basic example. This is the most basic example of asymptotic symmetries, that we have for gauge theories. So I'll just briefly plug a pedagogical paper that just explains this from like a sort of like undergrad, like classical perspective, like what the Noether, how the Noether charge like classically like tells you stuff about Bremsstrahlung, and just like works it out like sort of in a elementary style thing. So I'll just say that. So another important thing to note is that under a partial gauge fixing, so let's say Lorentz gauge, which is basically the best gauge for this discussion, the residual gauge transformations actually have to satisfy the wave equation. So you might be asking like, what's going on with this partial gauge fixing? What's the point of this? Well, so it's a pretty subtle story, but what I'll say is that in the beginning I said the asymptotic symmetry group is allowed gauge transformations which satisfy some sort of good fall offs divided by trivial gauge transformations. And the basic idea is that you can do a partial gauge fixing that if it's a good partial gauge fixing, it will get rid of all the trivial gauge transformations and say that, okay, those aren't allowed anymore because we've fixed them away. And then there'll be a smaller subset of allowed gauge transformations. But the idea is that if your partial gauge fixing is good, then the group in the beginning and the end will actually be the same. And this is the case for Lorentz gauge. So just to be clear, the reason that the trivial gauge transformations are gotten rid of with Lorentz gauge is that, if you have this function theta, which generates a gauge transformation, and it has to satisfy the wave equation, then, all solutions to the wave equation, kind of spread out on light cones, right? So if you have a little bump in the interior, it has to hit null infinity, right? So you can't have a little bump that doesn't go to null infinity. So that's why there are no trivial gauge transformations with compact support. Okay. So the sort of basic, the sort of most basic example of such a gauge transformation, that's sort of the Green's function for this whole thing, because it becomes like a delta function on the sphere at null infinity, is, of this form. This isn't too important, the exact form of this function, where Q is some sort of null vector. This becomes a delta function on the null infinity, which has a support just on the point that Q is pointing at. And anyway, this Green's function has a scaling symmetry. So if you have just a scalar S in a space-time point X, then you can just see based on the simple form of the function, if you replace X with S times X, the function itself won't change. And remember, so just to be clear, this satisfies the wave equation. This is like a special function, satisfies the wave equation, becomes a delta function at null infinity. And because this function has the scaling symmetry, it means that the function isn't really a function of all of the x's. It's just a function of, let's say, x, the spatial x over t. So actually, yeah. So if this is the spatial part of this, the space-time vector, then theta only really depends on x over t at large distances and times. So if you have some particle traveling on some world line, then it only depends on the velocity of that particle at late times and doesn't depend on like shifts. Okay, so that was U1 gauge theory. Better, or example people are more interested in is gravity. So in the case of gravity, there's a lot to be said about what the fall-offs of gravity are. I'm not really expecting you to digest this. I just thought I would write it here. But for 4D radiative gravity, there's these certain fall-offs, and there's this certain metric, the Bondi metric, which has different components that come in at different values in 1 over r. Whoops. And they have certain and there are certain relationships between some of these functions, but I'm not going to write them down. But the upshot of all of this, though, is that if you have these fall-offs, any sort of metrics satisfying, the Bondi fall-offs, what are the gauge transformations that preserve these fall-offs? And the answer is super translations. So here I've just written the first component, which mentally I think is like the most important to keep in mind. So what do we have here? Okay. So to reiterate, z is a coordinate on the 2 sphere. So we have a function on the 2 sphere, right? Basically at null infinity. And then we have an angle dependent u translation. That's sort of like to zeroth order. That's what like a super translation is. It's an angle dependent translation. And for instance, your regular time translations and the 3 space translations, those are actually all examples of super translations. So for instance, a time translation would be f equals 1, and then the 3 space translations would be the 3 spherical harmonics at L equals 1. And if I wrote the further 1 over r corrections, you could probably see it a little easier, but okay, so okay, good, right. And so likewise, you could have a Noether current and a Noether charge associated with the symmetry, and the corresponding conservation law is the soft graviton theorem for these super translations. So here's just a little image of how you can think of a super translation. Okay, so what's going on in this image? Well, we have null infinity here, and then we have constant u slices at null infinity, which are these 2 spheres. Well, in this picture, they're 2 circles. And then here, this red vector are the vectors of the super translation. So you can see that they're different length. They're pointing along u, right? This is partial u, and they're different. They have different lengths at different angles. So this is how you can picture a super translation. Okay, so that was everything I wanted to say about asymptotic symmetries. Are there any questions about this part so far? Cool. Okay, so now I'm going to give a very brief introduction to BFSS. So think about Kaluza-Klein, and this will be sort of very basic introduction for people who have never heard of this before. Okay, so recall Kaluza-Klein theory, just as in its original incarnation. So if you have a graviton in 5 dimensions, then you compactify that on a spatial circle. The modes, the low energy theory of that in 4 dimensions is then the graviton, the photon, and the dilaton. Okay, but if the graviton has n units of momentum around the compact dimension, then you'll have some 4D particle which has some mass, which will be proportional to its charge, which will have which will be proportional to n, which is the units of momentum. So 11-dimensional supergravity, okay, has 3 massless fields. It has a graviton field, a gravitino field, and a 3-form field. And if you compactify this on a small spatial circle, then you get all the massless fields of type 2A string theory. And then M theory is, defined to be the theory which is type 2A string theory when you compactify it. Okay, assuming that exists. Okay, great. So importantly, type 2A string theory has an RR1 form field, which I might call the photon at some points in this talk, which is denoted C mu. So a basic question you could ask is, what are the massive charge states under this 1 form field, right? Because when I said charge, I meant in my last slide, when I said these particles are charged, I meant they're charged with respect to the 1 form field. So what are these? And the only possibility you can really think of is D0 branes. So therefore, 11-dimensional gravitons in M theory with momentum around the compact dimension, these are bound state clumps of D0 branes in 10 dimensions, which is type 2A string theory. So then what happens if you boost this picture is the idea of BFSS. So here we have 11 dimensions, right? Here we have time, here we have the 10th spatial dimension, and then here you have a really tiny compact dimension, which I've called RC. And then if you do a large boost in the 0 and 10 dimensions, then here these lines are like lines that I am identifying with each other, right? So like this point is being identified, this line is identified with this line and so on. So if you do a large boost in this dimension, then then this space-like circle becomes a nearly light-like circle with some periodicity on one of these, null lines, which I'll call R. And the bigger the boost is, the bigger R gets. So proportional to like the parameter of the boost is how big R is going to get. And the idea is that if you sort of have RC, this is really small, but you boost it a lot, R can get bigger and bigger. And the bigger R gets, you can just recover the whole space again. So you can sort of play around with it by like taking R really small here, and then you get like this compactified theory. Then if you make R really big in the boost, then you get the whole thing back. So boost is big, you recover the whole space. Okay, so the Bfss conjecture, 1996, says that the light cone quantization of M theory is equal to a certain 0 + 1 dimensional quantum mechanical theory of n by n matrices when n is going to infinity, described by d0 branes moving in the 9 + 1 dimensional type 2 string theory. So that's sort of a lot to say, but the basic idea is that particles in different objects in the 11-dimensional thing, you can think of as interacting clumps of d0 branes in the lower dimensional theory. So for instance, gravitons are in the original incarnation of this idea, these are just the lowest possible energy bound state, like clumps of d0 branes. I mean, the d0 branes interact with each other, but there's like a zero energy one, and that's the graviton. And the idea is that if you have graviton amplitudes in M theory, that should be equal to these Bfss amplitudes of the d0 brane clumps. Whoops. Oh yeah, and I suppressed polarization data here, but there's these fermionic variables in Bfss, and that stores the information relating to the fermions. Okay, so to kind of reiterate some of this stuff, here, if we denote x plus and x minus as x0 plus or minus x10, and then we also have p plus and p minus, likewise for the 11-dimensional theory, then if you compactify x minus, right, like this direction here, if you periodically identify x minus 2 pi r, and then you have some sort of the overall p plus in the theory is going to be n over r, it's going to be quantized. And then if you keep this fixed and you take r really big, you also take n really big. So this is the idea. You have something going on in 11 dimensions with some total p plus, and it's n over r. And then if you take r really big, you get the whole space back, as long as you scale up n as well. And that's why n has to be proportional to, n has to go to infinity. Okay. So, right, in particular, I already said that. Okay, good. Oh, actually, no, I didn't say this part. So, yeah, so one interesting feature of these d0 branes is that they're non-relativistic in the lower dimensional theory. So why is this happening? Well, if you sort of take any old like 4 momenta and you boost it a lot, then the transverse momenta are going to stay the same, but the momentum in the direction of boosting is going to get really, really large. And the lower dimensional theory, the momentum in the direction that you don't see anymore, that seems to contribute to the mass of the energy of the particle, right? So the mass is getting really big, but the transverse momenta are staying the same, and so you're getting a non-relativistic limit. So these d0 branes are all moving non-relativistically. Okay, so here's like a basic picture of this setup. So what do we have here? So these 2 black planes, these are null planes, and they're being identified with each other. And then here are these 2 gravitons, which I've drawn in red and purple. and these solid lines are their total momenta, and they have some component, let's say, in the x minus direction, right? So yeah, these black planes are being identified with each other. The gravitons are moving like this. There's some transverse separation. They have some p plus components that are quantized. And then in the D0 brane world, there are clumps of D0 branes that are also scattering with each other. Okay, so the quantum variables, Bfss, are matrices. Okay, right. So then then you have to write down the quantum mechanical theory of non-relativistic D0 branes. So that's totally fixed by like all the symmetries of the theory. So you have this UN gauge symmetry. Actually, I wrote SUN here, but I should have wrote UN. Okay, so you have a UN gauge symmetry, and then you have 16 supersymmetries that it has to have. But I'll just sort of briefly say that. So for all the 9 transverse dimensions, you have I, which is the index for these 9 transverse spatial dimensions. You have XI, which are matrices, and this should say UN. And these are the different components. So here, XIA, those are just like numbers, and TA are the generators of the algebra. And then likewise, you also have fermionic variables with 16 spinor indices, and these are fermionic matrices. So states are then functions of these variables. And then I'll write down the Hamiltonian for BFSS. This equation won't be very, you don't have to know this, you don't have to understand this equation for the talk, but it's important to just know that what I'm talking about here. So this is the Hamiltonian for BFSS. And if you use the constraint that all the states have to be UN invariant, which is basically just that if you rotate the different D0 branes into each other, they're sort of like bosonic objects. The states have to be UN invariant. So this is the UN generator acting on a physical state. That has to be 0. So this Hamiltonian plus this constraint and these variables, that's BFSS. Okay, so I actually can't quite see this, what I wrote here. Sorry. Okay, yeah. So importantly, the bosonic potential for BFSS is if you sum over all I and J. Oh, there should be a squared there. Darn. Okay, there should be a little squared right here. It's just trace of the commutator of summing over all xi and xj. And classically, this will be at a minimum of 0 when all the matrices commute with each other for all I and j. So in this case, all the matrices are simultaneously diagonalizable, and thus you can write each matrix as just a bunch of eigenvalues on the main diagonal. And what the interpretation of all these eigenvalues is that they correspond to the positions of the n different D0 branes. So the off-diagonal terms for well-separated D0 branes are superharmonic oscillators with the frequency of the harmonic oscillator proportional to the distance between the D0 branes. So the idea is that if you have a bunch of D0 branes and they're widely separated, you have these diagonal terms which correspond to the positions of the D0 branes. Just in the normal quantum mechanical sense, this is literally like quantum mechanics, but just with a large number of variables. And then the each sort of off-diagonal cell is a superharmonic oscillator, and like the occupation number of that oscillator is just how many strings are stretched between, the ith and jth D0 brane. So this could be, if you would like, consider to be some emergent theory of space-time, because the space-time coordinates are sort of emerging from this like matrix, the eigenvalues of these matrices. It's also interesting to note that if you if you conjugate by certain UN matrices, what looks like, some D0 branes and some strings very simply in one basis of the matrix might have some really, really complicated description in some other basis. So sort of, I guess maybe there's some, I don't know, some sort of emergent choice of basis that arises due to some certain set of states. Okay, anyway. So okay, so now I've said that there are these D0 brane clumps. Okay, but why would they interact at all? So the idea is that the attraction of far separated clumps comes from the strings being in the ground states with some associated ground state energy, which depends on the relative distance and velocity of the clumps. So just to be clear, if you put a string in between these two clumps, then there's some potential energy that's proportional to the distance of the clumps, right? But I'm saying if you put that oscillator in its ground state, the energy of that state isn't exactly zero. It's something a little bit bigger than zero, and it's dying off with distance, and it's depends on the velocity of the relative clumps. But the idea is that if you just sort of picture two clumps kind of passing each other, so okay, think about like a quantum system being varied adiabatically, right? Like a particle in a box. If you start in one particular, if you start in the ground state and you like change the size of the walls of the box, then the energy of that ground state will change. Just as long as you slowly vary the walls of the box, you'll still always stay in the lowest energy eigenstate. Likewise, if you have two clumps which slowly pass each other far away, then the harmonic oscillator describing the strings in between these two clumps will also slowly vary, and that ground state energy, if you actually calculate it, will give you the potential between, let's say, these two clumps. So that's why they're interacting. Oh yeah, and I'll also just say a brief point, which it's good to just, I didn't actually know this before I started, I just thought it was kind of interesting, but it's just that the Galilei algebra is a subgroup of the Poincare algebra, not like a contraction, but it's actually a subgroup in one lower dimension. So I'll just briefly flash that on the screen here, but only in this null quantization sense. Okay, but okay, now let's talk about the paper. So the basic idea is as follows. In M theory, you can have 4 particles scatter in 11 dimensions, perhaps 4 gravitons with some finite energy. And that'll be described in the D0 brane language as some sort of clumps of D0 branes coming at each other. And then they, in principle, different D0 branes leave. And you could have one set of block diagonal matrices go into one block diagonal matrix go into another block diagonal matrix. So what does this look like if you add an extra soft graviton to this amplitude? Well, this looks like a small clump leaving one of the bigger clumps, right? So here it's it's a clump with like a small number of D0 branes leaving one of the other clumps. So the idea is that, so the potential, right, that the thing that was trace commutator squared, that has flat directions corresponding to like clumps separating. So whenever you have clump scattering, it's always possible for the wave function of this state to kind of leak out along the flat directions, and those can correspond to soft gravitons. So there's always the possibility for these soft gravitons to be emitted by any sort of scattering process. Okay, so just as a sort of basic table of contents for the dictionary. Okay, so the soft limit in M theory is when the energy of like the soft particle divided by the energy of any of the other particles, right? So here omega is energy, S stands for soft, so the soft graviton's energy, and J is just labeling all the other particles. So when the ratio of all these things goes to 0, that's when one particle is soft. And in Bfss, that's when one of the sizes of the blocks is much smaller than the size of the other blocks. You can also rewrite the leading soft graviton term in terms of these Bfss variables, and it ends up being an inversion tensor, but I'm actually not going to talk about that in this talk. It's not too relevant. But yeah, the subleading terms, instead of being expansions in terms of this ratio of energy of the soft particle divided by energy of the other particles, they're going to be expansions in terms of 1 over n. And the asymptotic symmetry of M theory, which would be super translations, would be large gauge transformations of the RR1 form field. So this is maybe the most obscure result in the paper. So yeah, so there's this interesting, yeah.
Do you mind if I ask about, sorry, that last one?
Yes.
So the Ramon one form gauge field is sort of like a background field for BFSS. I mean, it's not a thing in BFSS. So I'm a little bit confused about what that means or why it's in the BFSS column.
Yeah, so this is completely true. So you have to put in a background, a pure gauge background one form field in to couplet to BFSS. Now, this is like, so just so, right. How do I say this? So it's sort of, so even though it's like a strange incarnation of the symmetry, the statement is like true. Like it's, we showed it was, you know, true in the paper, and I'll like discuss a little bit of it. Now there's this really interesting.
So you're saying to consider the BFSS model with this pure gauge background, and then that would give you, I guess that would give you some other terms in the model.
Oh yeah, absolutely. That's from your paper actually.
Yeah, so that sort of naively different model is now just okay. That's like
so,
what you get after the super translation.
Yeah. So
okay.
There's this interesting. So this wasn't so okay. So you can also rephrase soft symmetries just in regular quantum field theory in this way. Like you can quantize them with respect to certain backgrounds and then like turn on a background that's like pure gauge. And so for instance, when we write out a mode in a textbook, when we write out a mode expansion, like a mu, it's a mode expansion thing. You could also then say it's a mode expansion plus some background that, like, let's say is pure gauge. But funnily enough, the background is sort of still in the theory, just you get to it by inserting an infinite number of soft particles that like can move you around from one background to the other. So soft particles can move you from one vacuum to another, right? That's the thing, you have infinite vacuum degeneracy. So this isn't something we were able to figure out in the paper, but this is something I think very well, this would be like really interesting if there is some sort of sense in which this is also true in BFSS for what we're saying here. So just to like say my very you know, not worked out idea, but the idea would be something like, you know, oftentimes when we do things in BFSS, we like actually have matrices and think about an n by n matrix and think about n getting really big. But it's certainly possible that, you know, in the n goes to infinity limit, there's some sense which that might not actually correspond to degrees of freedom in an actual matrix. So for instance, you know, you could have certain infinite dimensional matrices that aren't diagonalizable and could have states which are not, which could have, you could have matrices which are not really describable in terms of, you know, the D0 branes themselves. So it's conceivable to me that there could be some sort of state in the literal n equals infinity version of this model that does actually correspond to, you know, an infinite number of soft D0 branes somehow, which move you from one vacuum to another, and which somehow is turning on this pure gauge background field. But that's not in the paper, that's just me talking. But but that sort of exact kind of phenomenon happens in like quantum field theory, where you can perturb around different backgrounds and you know, get to those. You can consider theories perturbed around different pure gauge backgrounds and get to them via the insertion of an infinite number of soft particles. And that very well could occur in BFSS as well. Now, this paper is really just like the zeroth order. Like this, so just remember, like in the first slide, I'm just like, what are these things in BFSS? Just like zeroth order. What are these like duality things? So soft gravitons are like small clumps, and the super translation symmetry is the large gauge symmetry of the background one form field. Now, is there some way you could transform the background field into like some actual dynamical thing in the model? I don't know the answer to that, but that's, I think, probably a really productive like train of thought to pursue. But just to reiterate, like we were just happy to like like definitively answer like how are like super translations manifest like in BFSS. So that was because I mean that was a question that had not been asked. So
Okay, yeah, that makes sense.
okay, cool. And does anyone else have a question?
No, can I ask something?
Yeah.
So as far as I remember, okay, the spectrum is continuous in BFSS, but there is still this question whether the ground state is unique or what precisely is the ground state, right? Or if there is any degeneracy. This is not solved yet, right?
Sorry, ground state of BFSS?
Yeah, there is this old question, right? From the past.
Well, ground state of BF, do you just mean like if you have like a D0 brane clump that has zero energy, like the marginal?
Yeah, I mean, there are all these flat directions. So what precisely is the ground state? I guess
Well,
it's
wasn't that, well, I mean, famously for n equals 2, that was solved by Sethi and Stern.
for SU2, yeah, for n equals 2.
But then but for bigger n, so I mean, basically the way these, they just always like calculate the index, right? And show the index is, not 0, right? And then show that that state exists. So the index, I mean, there were lots of papers by Gregory Moore and other people where they did calculate these indexes for other n and found that, these states exist, right?
Yeah, I think the main thing is just not the actual ground state wave function is still not known.
Oh, yeah,
I'm not sure if that's important for you or not.
Yeah, exactly. I mean, in order to see, yeah.
Yeah, the ground state wave function certainly isn't known. Yeah. So, right, so okay, everything in BFSS is like either like really complicated. Everything is really complicated. So if you're gonna write a paper about it, you either have to get really complicated or be really simple. And luckily for us in this paper, we didn't really need to use the complicated stuff of BFSS. Somehow everything ended up working out. So we could just use like simple features of it without having to get down and dirty. Okay, yeah, but I don't know, does that answer your question? Or?
Yeah, okay, I just wanted to make sure that this problem didn't cause any concern in your analysis, but okay.
No, yeah. Anything else or anyone else? Okay, cool. So, yeah, so, right, so actually there was a point I was making before, set of very good questions, but just that if you have two clumps which scatter off each other, there's always the possibility for one little clump to go off along one of these flat directions. So this is like exactly the sort of scenario covered by the soft graviton theorem, right? So, we don't prove the soft graviton theorem in BFSS. We're just using the BFSS duality and saying, okay, we know that the soft graviton theorem is true in M theory. Let's assume that this conjectured BFSS thing, which has some evidence for it, is true. What conclusions can you draw in BFSS? It seems more likely that the soft graviton theorem would tell us something about BFSS than that BFSS would tell us something about the soft graviton theorem. And the scattering of these clumps and the small, clumps coming off of them, that's like the exact scenario discussed in the soft graviton, or addressed by the soft graviton theorem. And infrared divergences, which come from all these flat directions in BFSS. In other words, there's a linking of these two infrared divergences used in two very different senses, right? One just comes from infinite volume flat directions. One comes from low energy, gravitons. So there's clearly some sort of link there. Although, once again, this wasn't something addressed in the paper. But food for thought. Okay, very good. So what is the soft graviton theorem? Well, if you have a scattering amplitude, and let's say these are a bunch of finite energy particles with momenta k1 through kn, and then we insert a soft graviton momentum qs and polarization tensor epsilon sub s, then this amplitude is just modified by a phase, like infinitesimally by a phase. So like if you, just in the sense that multiplying any number is like an infinitesimal phase. Where here we have the polarization of the soft graviton, and then here eta j is just whether or not the jth particle is incoming or outgoing. So for an incoming particle, eta j would be -1. For an outgoing particle, eta j would be +1. And then here have this soft factor. And you can think about a phase shift on all of, on this amplitude as just being a phase shift coming from the super translation. So in other words, if you have particles in momentum space, if you have particles in momentum eigenstates, and you're going to null infinity, and you do these, U translations, right? These angle-dependent U translations that'll shift the wave function, the plane wave, each plane wave by a certain little phase, and those certain little phases are just given by this factor. So this factor is the phase shift from the super translation on all the particles. Right, okay, so actually, let me not talk about that. Okay, well, so this slide I had for, yeah, maybe this slide wasn't too good to include. Well, okay, this purposes of this talk. Oh, well, okay, well, I'll just say briefly that if you parameterize null momenta in this particular way, that's like very amenable to Galilean symmetry. So what is this? So VI is a vector in the 9 transverse spatial dimensions. And then if you parameterize the polarization tensors also in a certain way, given by derivatives of this sort of polarization here, then you can, this is like, this sort of parameterization is just very useful for like null slicings. And you can rewrite the polarization tensor in this new basis given by I and J, which are like the transverse dimensions. So V is sort of should be thought of as the velocity in the Galilean world, the non-relativistic world. And if you just rewrite this soft graviton factor in terms of those parameterizations I was just telling you about that are very amenable to studying the non-relativistic null slicing world, then you get the following factor. So what's going on in this factor? Well, here we have kappa, which is just the gravitational constant, which is basically square root of g. Then we have the size of the block divided by the size of the small block, so the small graviton block, which is supposed to be getting much smaller than this one here. Then we have the polarization information of the small block. Then we have some combination of the velocities, which are being contracted with the polarization information. So I'll just say also that this combination is like the inversion tensor from conformal field theory. Strange. Okay, okay, but the really important thing about this expression is the proportionality to NJ, because that's the charge of the D0 brane clump, right? Just the number of D0 branes in that clump. So when we have an expression like this doesn't look like the soft graviton theorem. This looks like the soft photon theorem, where we have this dependence on the charges of the different particles out front. Okay, so just from literally like plugging in the velocities of the D0 brane clumps into the soft graviton theorem, you already get something that's looking like the soft photon theorem. And that's going to tip us off to the fact that, super translation symmetry is actually this one form symmetry in BFSS. So, right, so what is the asymptotic symmetry group then of non-relativistic gauge transformations of this one form field? Well, the sort of guess, which is actually not really a guess, but really inherited from the 11-dimensional super translation story, is that they can only depend on x over t, right? So I'm just talking about this function theta, which parameterizes a gauge transformation. This is a gauge parameter. What are the boundary conditions you want to put on this thing non-relativistically? Well, it should only depend not at large t, it should only depend on the ratio x over t. So to my knowledge, there wasn't anything written about non-relativistic gauge transformation, boundary conditions in the literature before this. I mean, anyone can correct me if I'm wrong, but this seems to be the sort of right definition that's inherited from the 11-dimensional thing. Right. So earlier in the talk, I was talking about, U1 gauge transformations and how if they satisfy the wave equation in Lorentz gauge, they have to depend on x over t because they're kind of spreading out. This is just like inherited from that discussion. So, okay, what do we have here then? Well, here we have a little cartoon of d0 brane scattering. So here we have these sharply peaked in momentum space Gaussian wave packets of clumps, and they come in from infinity, and they have a small angular width, and then they go into some scattering zone where they scatter in any which way they like, and then clumps with different numbers of d0 branes can come out. And the idea is that if we have this function sort of living on this whole picture, theta of t and x, such that only depends on x over t, so it only depends on these lines passing the origin, then it takes a well-defined value on each clump, right? Because the clump has a small angular width. So one of the members of the audience, Mark, had a paper with Washington Taylor a long time ago where they explicitly said, okay, how do you couple Bfss to background fields? And they gave it for like all the background fields, but we just wanted it for the one form field. So if you take this term in the action this term in the action will couple Bfss to a background one form field, to the d0 branes. So here, okay, so what's going on here? So we have a sum over, all the integers. Then we have derivatives of the one form field at the spatial origin. And then we have this other term here, I mu, and different moments of I mu, which is given by this fall. This part isn't, I should say this part isn't like super important for just like casual audience members, but it is sort of like one of it is how we got like the main result for this like one form field. So, okay, what are these moments? So this is a term which has to respect all the symmetries of Bfss. So it has to respect the gauge conjugation symmetry by UN matrix, which it does because we put everything here in a trace. So here we have a trace over a symmetrized average over all possible orderings of this matrix. So we're just symmetrizing, all the sum over all products of these matrices here. And here we have I mu, which is just the velocity vector. So here, because it's non-relativistic, it's just here we have 1 over r. And then here we have the velocity of this matrix x dot, and that goes in there. Then we also have a fermionic term, but the fermionic term doesn't actually contribute to our story. So I'll just say very briefly about this fermionic term. There's a symmetry of like reparameterizing variables in Bfss where every term has a scaling dimension that you can assign it. And then if you scale everything with certain dimensions, the action will not change. And likewise, the physics of the situation will change. And, d0 branes have their own, electromagnetic field, under this one form thing. You figure out what the scaling dimension for this electromagnetic field is, they could come, which could come from another d0 brane or it could come from the background field. And you figure out the scaling dimension for this, background, electromagnetic field. And then you figure out the scaling dimensions for the fermions and everything. And you will find that they actually, well, so for, see, this is a bit of a mouthful, but for electromagnetic fields, which are pure gauge transformations of this form, so they're functions x over t, and then t is getting really big, the more derivatives you have over such a function that's like x over t, each derivative here is bringing out a factor of t, and then the x's are getting big, the fermions are just staying themselves, and the more fermions you add, the smaller those terms are going to grow with t. So the fermionic terms don't actually contribute in this scenario that I am describing, because the functions are functions of x over t. So that's what I meant. That was one of the things I meant when I said things actually got sort of simple for this story. Okay. So here I have a matrix. This should be thought of as like one of those matrices xi. And here you have different clumps. And then here, just if you think, I don't want to say classically, but okay, but here, okay, how should I describe this? Okay, I haven't given this talk yet, sorry. Yeah, so states are functions of variables. And a sharply peaked wave function, a sharply peaked wave packet will only have a non-trivial value on values of like a certain width, right? So what are the classical variables of this classical matrix for which these widely separated wave packet states take on a non-trivial value? Well, because all of these terms in the block correspond to just say like the dynamics of the block modulo the center of mass motion, right? So all the stuff on the off diagonal terms, but in the block will just stay constant as t is getting bigger. These diagonal terms, which correspond to the center of mass motion of the block, those will get bigger with t. Everything else will actually be shrinking because these correspond to the superharmonic oscillators of the strings on the off diagonal terms. As these wave packets get further and further away, the frequency of those superharmonic oscillators will grow with t, and the size of that wave function will shrink, like the width will shrink as 1 over the square root of t. So these things in this light gray area are all going to 0. This middle gray, these are staying constant. These darker ones are growing with t as the velocities, increase the center of mass position over time. And this is all to say, so let me just say that this sort of assumption that we have scattering in the BFSS world of this form is really what we needed in order to, get physics out of it, right? So we didn't have to muddle into the very complicated world of, computing very detailed dynamics with BFSS, because we assumed this sort of basic picture here. We have different clumps, we have wave functions, different widely separated wave packets going different spots. And then we have this interaction term, and we assume this form for this very reasonable form for how the scattering looks. And therefore, you put all this together and you get that if you take an BFSS amplitude in one of these backgrounds, it's related to the amplitude in a 0 background, but now with this phase factor here. Because, yeah, I mean, here I replaced x over t with the velocity of each clump in this parameter theta here. Sorry. And once again, this factor just comes from like e to the I of this factor when you assume the following form for the initial and final states, right? Because this factor will become a pure total derivative in time. And then, okay, I think I might have lost some people. Does anyone have a question about any of this? okay, so let me say this again, but in a slightly different way. We're coupling this term in the action to the BFSS action. But here we're assuming that C mu, right? C mu is a total derivative of a function theta that only depends on x over t. Now, if you plug in a total derivative for C mu here, well, this term, you can rewrite this as actually a total time derivative of a certain term that only depends on the initial and final states in the wave function, right? Because you have a quantum amplitude, it's described by a path integral where you integrate, where you convolve the path integral over certain wave functions, initial and final wave functions. Now, what are the classical variables of the initial and final wave functions, where this wave function takes non-vanishing value, right? If you have like a sharp peak, then you can basically just, in the path integral, just replace convolving over this wave function of a sharp peak with just like the value at the center of that peak. And for these scattering states, the values look of this form where you have the velocities on the diagonal, which would just be v times time. Then you have these constant terms which don't grow in time, for describing the rest of the dynamics of each clump. Then you have these terms in the off diagonal which are going to 0. And thus, if you assume such a form, only basically each of these terms here will basically just be like v to the n or something. And then each of these become like a Taylor expansion for theta. And therefore, the whole thing simplifies to just being theta evaluated at these different velocities. So that was sort of what I meant when I said we proved that super translations are turning on background CMU fields. Right. So in other words, if you have a certain gauge parameter, which is defined by the polarization information and velocity of a specific soft clump. So here, we've written it right here. So here, this polarization information and velocity of the soft clump, it's a function of x over t. Then this is the rewritten soft graviton theorem in BFSS. So we multiplied by this prefactor here with the size of this small clump over R, which we're just sort of getting rid of. We're just sort of multiplying by like the pole. We're getting rid of the pole here. And then here we're generating a phase given by turning on this background field of the specific gauge parameter, from this particular soft graviton we're inserting. So in the celestial CFT world, we like to say that soft particles generate these large gauge transformations, because in the sense of like conformal field theory, if you like insert the operator that like creates a soft graviton like on the sphere or something that that generates like the action of the asymptotic gauge symmetry and like all the hard particles. Well, that's exactly what's happening here. Here we have the soft D0 brane clump, or the small clump, generating a background one form field that's pure gauge on the rest of the clumps. So it's true, as Mark said, that this isn't like fully taking place within BFSS as defined, because that doesn't have any background CMU field. But I think it's extremely suggestive that there could actually be, because, okay, the thing is that we have the left-hand side has no background field, but the right-hand side does. See, so the left-hand side is only taking place within BFSS as originally defined, but somehow the right-hand side is taking place in this world with a background field. So somehow, if somehow you could actually already kind of see that like putting in this like soft clump is actually kind of generating this background field. Now, could you show that? Now, a very interesting question would be, how would you show that, without appealing to like the soft graviton theorem, right? Because here we've used the soft graviton theorem, used the BFSS conjecture and rewritten everything. But could you show, how would you show that like within matrix quantum mechanics itself? I'm not sure. It would have to have something to do with the matrices being infinite dimensional and something weird there. I don't know. But yeah, I will say though that this is, to my knowledge, the only example of a duality of what's kind of interesting about this example is we have an asymptotic symmetry and a duality, right? Duality in the sense of, something in higher dimension related to something in lower dimensions. And the asymptotic symmetry in the higher dimensions, which was super translation symmetry, is related to an asymptotic symmetry in the lower dimensions, namely the one form symmetry. It's very strange, actually, that the super translation in 11D are totally captured by large non-relativistic gauge transformations in 10D, because how am I in time? Oh, darn, I didn't realize I had gone over time. But this will be my last point, that if you have just standard Kaluza-Klein theory, where you're compactifying on a spatial circle, right? A graviton in the higher dimensional theory will be a graviton plus photon plus dilaton in a lower dimensional theory, which depends on the polarization of the graviton in the higher dimensional theory. So it would stand to reason that the soft graviton theorem in the higher dimensional theory would decompose into like the soft graviton plus soft photon plus soft dilaton theorem in the lower dimensional theory. But somehow in this example, there's no graviton or dilaton to be found. Actually, the full asymptotic symmetry is 100% captured just by this one form field. And I also don't have I don't understand myself, like the reason for this. Like we've shown it's true, but it's very strange to me. Like you would think that, the graviton would have like more gauge symmetry or something, but somehow the fact that this is non-relativistic is like somehow doing some of the work for us. I don't know. Anyway, thank you very much for listening. Hopefully I have both described well enough what happens in the paper, but also said some interesting avenues for further thought in this project. I very much think that this project is like a 0th order thing. Like what are like very basic objects of asymptotic symmetries in BFSS. And I think it points in like actually very rich like directions. There haven't been that many papers on BFSS for about like 20 years, except for some interesting ones, but there used to be a lot of them. But it's, I think, possible that, now we've learned some stuff and, there's maybe interesting stuff to say about BFSS. A lot of interesting stuff happens in it. I think this is like a good example of something interesting that could happen in it that people weren't thinking about before just because, not enough time had passed. So anyway, thank you very much for listening.
Thanks for the very nice talk. Any other questions for Noah?
I do have a question. Thank you for the talk first. So the formula you derived in the end is a formula that you can obtain by assuming the soft Graviton theorem in M theory, and then working out the holographic dictionary, and then you obtain this frame formula, right? Yeah. But you also have an expression for these amplitudes that you can compute. Did you check that this formula is true, or it's just a conjecture about what the amplitude has to satisfy?
It's a conjecture which is exactly as strong as conjecturing that the BFSS duality is true.
Okay.
Yeah, which I mean is actually a somewhat interesting question. Like if it is true, I mean, okay, there's some evidence for it, but at the same time, like one would hope there's like be more evidence for it. But I mean, that's like a whole other can of worms. the one thing this paper assumes is that the BFSS conjecture is true. That's it. Yeah, so I mean, the BFSS conjecture in the strict sense of, yes. Okay, this equation here, right? In the sense of scattering amplitudes of, let's say, gravitons in M theory are equal to scattering amplitudes of clumps in BFSS. So if you assume, this particular equation is true, then like the soft theorem just in terms of M theory in 11 dimensions will also be true of BFSS. That's what I mean when I say, you're assuming that.
Okay.
I understand. I also understand in this group, there's like been work on matrix models of gravity.
Oh yeah. Indeed.
Does anyone want to comment? I mean, I don't know too much about this. I'd be interested for someone in the audience to comment to me, like what they think the relevance might be, if there is any, or.
Well, it's a bit unclear to me how to connect the two stories right now. Personally, the set of words are the same, but the observables are a bit different. So I mean, in our model, we do have large gauge transformations. We do have asymptotic symmetries. They're basically the flat space equivalent of the binary diffeomorphism symmetry in JT. You can, this symmetry is broken. So I mean, our model our bulk is two-dimensional. So the large gauge symmetry is broken, which is a specificity of low dimension. So yeah, I'm not sure exactly what would be the immediate connection, but maybe there is.
Yeah, I mean, I guess there's something.
Oh, and our dual model is a matrix model. It's not a matrix quantum mechanics.
Right. I mean, so there's no sense in, not this picture. I mean, there's no sense in which like some sort of, I mean, picture like this where you have like you have a matrix with like blocks and then like a tiny block, like that could be some sort of.
So in our model, the dictionary that you have between scattering states in the bulk and matrices does not exist. We don't have this. It's not the same dictionary.
Right.
Matrix plays a role that is very different than yours. Yeah.
Okay, cool.
But so the dictionary involves let's see. And on the boundary of your theory, the objects, the observable that you map bulk amplitudes to is also can be seen as a scattering experiment also for the binary theory, right? It's just a non-relativistic one.
Mm-hmm.
So is it so surprising that there are also sub-theorems for this? Because you seem to be surprised by the fact that bulk sub-theorems map to binary sub-theorems, but since the binary observable is an amplitude and that you have a gauge symmetry in this binary theory, I'm not sure why were you so surprised by this?
Well, the thing that surprised me, well, was just the idea that the gravitational diffeomorphism symmetry in the higher dimensions was completely captured by the photons gauge symmetry in lower dimensions, right? Because I would have expected it to decompose as some sort of, sum of graviton, the graviton, photon, and dilaton, those all exist in type 2A string theory, right? So in principle, I mean, I totally would have expected those all to play a part, but it was just the photon. That was what surprised me.
So it's not the fact that it maps to another asymptotic symmetry, but sorry, another subtheorem, but it's the fact that only one type of symmetry contributes.
Yeah.
Okay.
Yeah, exactly.
Any
Okay.
other questions?
Thank you.
I can't see who asked that question, but I think we met, right?
Yeah, we met.
Jason, okay, yeah.
Charles here.
Charles.
Oh
Charles.
yeah. Okay, good. Hi, Charles.
How are you?
Good.
Yeah, we met at this celestial holography conference. I'm happy I had the longer version of your talk.
Thank you.
Now, I mean, this one being the longer version.
Right.
The first one was pretty short. So.
Okay, if there are no other questions, let's thank Noah again.
Sorry, I was still formulating a question, but
Oh.
let's see. So, yeah, I guess my question was about the different kinds of particles in the supergravity multiplet in 11 dimensions. So you have gravitons, but then also other kinds of particles, the coming from, I guess, the three form fields and fermions and things like that. And so it seems like you should have a soft graviton theorem and then also a soft gauge boson theorem somewhere in there, and maybe they're kind of the same thing. I'm just wondering if you can see that in this way of thinking. So
Yeah.
do you see these different soft theorems kind of coming together, and is it like the same derivation from Bfss or not? And I guess in Bfss it's just like what's going on with the fermions in each block will tell you what kind of particle you're scattering. So
Yeah. So, whoops. So right. So you have also the gravitino, and then you have the three form field. So I always kind of think back to this kind of picture of you have these hard particles, so there's two components. Okay, right. Sorry, let me actually go one thing back. Okay, so what always tends to happen with these soft charges is you have like the soft part and then you have the hard part. So the soft part only pertains to, in this case, the electromagnetic field. It would pertain to the massless particles in general. And then the hard part pertains to like all the stuff charged, all the stuff that like interacts with these like massless particles. So here we have in blue like the hard particles, and in yellow like the soft particles. So for the three form, so higher form fields and like asymptotic symmetries is actually like a very subtle story, which I don't think has been fully like satisfactorily understood. Like there are papers about it, but if you just think about it just like in a very basic way, the things which are charged under like a three form would be not this one-dimensional world line, but a three-dimensional world volume. And in order to get like a non-trivial story, you would need to have like these world volumes sort of hitting angles in non-trivial ways. So already like this, so actually already, well, here's another way to think about it. So if I can get the soft gravity, okay, right, the soft graviton theorem and just the way it's written in like a textbook, for instance, here we have this we have a polarization vector here, right? Epsilon mu nu, and then it's being contracted with k mu and k nu for the hard particles. This is a symmetric tensor for a graviton. If this was anti-symmetric, it would just be zero. So I think there's reasons to think that like the leading, I don't know if they have, yeah, I'm not actually sure. Do they have leading soft theorems? I'm not sure.
Yeah, I don't know.
But yeah,
Maybe not.
so they might have, I think what is very likely the case is that they don't have leading soft theorems, but they have subleading soft theorems. And so there might be some story, it's just more subtle. Now for so that's for the three form field. For the gravitino field, yeah, funnily enough, like massless fermions don't have asymptotic symmetries like massless bosons do.
Yeah.
They have soft theorems, but they don't have their own asymptotic symmetries. That's its own story. So yeah, basically, I don't know. Basically, I think it's very likely there is a story. It's just subtler than the one
Yeah.
I presented here, which was just most basic leading soft graviton thing.
Okay. Thanks. Okay. I'll clap again, but yeah. Thanks. Okay. All right.
Okay, great.
Yeah, nice talk. So nice to meet you.
Thank you. Your paper was at the center of it all. Yeah.
No, it's funny that, yeah, that was like my PhD thesis, or
Really?
part of my PhD thesis. So
I didn't know that.
one of the first projects that I worked on.
Turn off the